So, good afternoon and welcome to the second lecture here in the 2DV604 software architecture class. Today we're going to talk about communication and documentation of software architectures. The first part is more of a recap from last week. Remember that the main reasons why we're even considering architecture is that our systems are growing and growing, and we put higher demands on the type of services and the qualities of these services, and we are adding things like mobility, we're adding things like awareness of where you are, where your devices are located, etc., etc. So at some point we hit the roof of human capability, that it will be extremely difficult for us to reason about and discuss these systems if we don't find a level of abstraction which really targets these types of questions. So software architecture is well, an abstraction that focuses on what a system should provide, and also to some extent how it should be organized and what type of support it should have for specific qualities. It's not that focused on how things will be implemented. The how is left for later in the development process. So we can say that to some extent it hosts functionality. That is, that we try to distribute responsibilities on various parts of the system. However, distributing responsibilities to various parts of the system require that we, in order to maintain this integrity of a system, discuss the responsibilities for the entire system first before we distribute into parts. So one example here that needs to be sorted out before we distribute responsibilities is certain qualities. The fact that performance is not a concern that affects just one part of the system or some parts of a system. The overall performance for a system is typically something that the entire system is responsible for. That's why we have to think about a concern like performance, how we should guarantee, in which way can we structure a system, which type of support mechanisms can we include in a system in order to come up with some kind of guarantees that the system will actually achieve the performance requirement. As I said before, the reason, the motivation for architecture design, that level of design, is the system complexity. We need to be able to reason about these things early in our development. We cannot postpone these system level concerns. We must deal with them before we decompose our system into subsystems that can be dealt with separately. So, last week we focused on stakeholders, their concerns, and how we describe how the architecture addresses this concern or these concerns in a view. We talked about that these concerns, they can appear and become relevant or irrelevant throughout the life cycle, throughout the system's life cycle. So from the very first day when the basic idea pops up until very late, right just before we actually decide to deinstall and decommission the system. So architecture is important throughout, which means that it must be a very flexible tool. So we talk about something up here, which should be able to be used early, but also late in the life cycle. So what we will talk about today is, in fact, communication and documentation. And communication and documentation is really trying to support all different activities that may occur in a system's lifetime. So the picture you see here at start up at 1 o'clock approximately with a new product being developed. This is of course a very simple oversimplification, but you can see that architecture is relevant here. Because here is where we make these decisions about the software system. We need to decide upon functionality, qualities, and which parts of the system that should be responsible for these functionalities and the realization of the qualities. When we deploy a system, well, architecture is also relevant for deployment. Which parts should go where on the physical or virtual hardware? Well, depending upon how we deploy our system, we will, well, provide for or make it more difficult to achieve certain qualities, to address certain concerns. After deployment, well, we can debate on this forever, but a simple view on things is that now the system goes into maintenance and support. And maintenance and support is like, well, we might migrate, we might port services, we might enhance and add features. And that will go on and on and on and on until we at some point decide that, well, we will no longer use this system and no one else will either. So we remove it. But architecture is relevant in all these steps, in all these activities. When we talk about product development, well, typically we need a tool to communicate among the developers, but also document so that we can have support for asynchronous communication, if you excuse this analogy, that we actually want to communicate in between groups, so that some group that needs to figure something out 5 months later, well, instead of communication directly with the architects, they can go to a document, some sort of documentation. Maintenance, well, people say that approximately 80% of the resources you invest in software, that's spent in that on activities, which is like from 3 o'clock to 9 o'clock approximately here in this wheel. So what do we see in the latter stages of the life cycle? Well, of course, the people that were involved originally in the new product development here, they are no longer around. They left for a new job, they left for another position in the organization. So the architecture documentation is part of the organizational memory. Okay. So there's definitely two perspectives here that we need to think of when we talk about documentation and possibly also communication of software architectures. One is, well, the fact that we make decisions up front that are important for all parts of a system. You remember that we make a decision about how to guarantee performance. Well, that is something that all subsystems in the system must consider when they do their detailed design work, when they do their implementation work, when they do their testing activities. They must consider these overarching decisions. So that is a kind of communication that this is the architecture to be. This is the architecture that we should build. Okay. But then at some point, it becomes more of a descriptive document. This was the architecture, or this is the architecture we have. Because the architecture, I mentioned it a couple of times now, it's relevant throughout the life cycle. So we use it to communicate, do this, and to communicate, it looks like this. Two slightly different perspectives. The most important thing to communicate with your architecture documentation are the decisions, the architecture level decisions. Why have we decided to decompose the system in this way? Why have we decided to use this authentication mechanism? Why did we decide to allocate the authentication responsibilities to that subsystem, and why did we decide to use that protocol? The decisions should be based on engineering principles. So proven knowledge and analysis. Shouldn't be, well, I think this works. People don't build bridges like that. If we do it like this, we think it works. We shouldn't build software that way either. So the decisions are important. What leads up to a certain decision that, combined with all other decisions, gives us the architecture? That is important, because think about 3 years from now. Someone starts to question a decision you guys made, and that decision was based on a thorough evaluation of alternatives. You did a performance model that actually formally proved that this was the most performant architecture. And then a fresh university graduate starts at your company and thinks that no, this can't be the best way. I want to play around with this and I want to change the architecture. Well, if you have a documentation of your decisions, well, people can look at that and see that, well, we better think twice about this, because these guys, they actually spent some time on this decision. Compare that to a situation where you just show a box with a couple of lines, 1 or 2 sentences that describes the box and these lines. The organizational memory will not recall why it looks like this. But that's actually what's most important, the why, in these parts of the life cycle. So I showed you parts of this documentation standard last week, and the focus was on the stakeholder and the system concerns. Okay. You can see there that the stakeholder has an interest in a system. And the association class there is a system concern. So this is really important when you work with architecture documentation or architecture communication. Who are you communicating to? Are you communicating to your peers, or are you communicating to end users? Are you communicating to management? Who is the target of your communication? Who's the target of the documentation? And this is something that we're going to emphasize today. The importance of a thorough stakeholder analysis and the importance of identifying the concerns these stakeholders have. Because that is as important as the requirements. We told you so many times that if you don't get the requirements right, you will not make your customers happy. The concern for the stakeholder, that's a requirement. If you don't get that right, the quality of your documentation will be low, because you actually document something that no one is interested in. So we will focus on these parts. So the 42010 framework, which is this part of the documentation model here is taken from. That document is really, well, it's a standard, but in fact I would say that this is a usable standard. Standard documents tend to be, well, very difficult to use. But I believe that this one is the exception from that rule. At least in my world, it is useful. So, for the stakeholders, for the concerns, well, what should we communicate? Well, we should communicate the results of the design decisions. Sometimes we should say more about the rationale, why we came up with a specific decision, than in other situations. I would say that if the stakeholder is directly involved in development or is directly involved in one of the later stages where you have maintenance, enhancement, porting, etc., well, then it's more important that you document the rationale, why you came up with the decision, compared to if you show something to management. They could ask questions, why does it look like this? But typically they are more interested in what. So this is another dimension you have to consider when you define your documentation and how to communicate your architecture. But the decisions, what is a decision? Well, what is an architectural decision? What is it that distinguishes or separates an architectural decision from a regular design decision? Well, this is important because architectural decisions should be documented in the architectural documentation. We should stay away from the design decisions here. So, I would say that there is really no exact rule here. And as you will see later, the problem here is that any design, all designs are hierarchical. So a system of subsystems where each subsystem contains additional subsystems that contain subsystems that contain. So it's very difficult to say that, well, at this level of abstraction, it's no longer architecture. So we will spend more time on thinking about the impact. What is the impact of your decision? Is it local or is it global? And global or close to global, I should say, they are then considered architectural decisions. So, architectural decisions, that's a creative process. That is where you create. As a designer, you create the system that you envision, the system that satisfies all the concerns from your stakeholders. Software requirements, functional requirements, the non-functional or quality requirements, all these are considered and you come up with something that meet those expectations. When you make your decisions, typically they are domain-based. They are somehow influenced by the domain you're currently working in. A huge influence is your personal experience. Say that you have used a specific type of database manager, a relational one or a text-based one. Well, say that you were involved in a project that, well, crashed and burned. And the problem there was that the database was a bottleneck. You couldn't really manage to get out of that tar pit. A year later, you're involved in another project, and you're currently discussing the type of persistence, how you should solve the persistency in your application. Your personal experience says that, I was involved in this project a year ago where you used relational databases and we had huge problems with performance. It's more likely that you will advocate an alternative than if you had been involved in a successful project where the database wasn't a problem. And this is, of course, a natural thing. However, it's not very engineering-like, because engineers, we should strive for some kind of objective evaluation, because it could well be that for this application in this domain, relational is the perfect match. I often hear that from this or something similar from freshly baked students, that when they get their first job, they can get in a position where they have to work with old technology. And they say that, oh, you know, they're using this ancient technology here. If we just move to, and then they enumerate all the latest technologies that they read about or maybe even worked with in the final year of their education, everything will be sorted out. However, throughout the life cycle, there is a continuous process. Is it worthwhile to port and migrate this, or should we sit still? Well, that decision is an objective one, and the freshly baked student would probably have advocated that we should move to this new technology. That's just an example. It could be that the student is right, by the way. Let us seen that a couple of times too. So here are some examples of architectural design decisions, just that you get a flavor of what it can be. Technology. Sure. Like we're using this framework, we're using this programming language, we're using this communication protocol, etc. Did the decomposition of your system into subsystems? like the first level decomposition that you guys are working with. The mechanisms that are cross-cutting these subsystems, all of them or a majority of them. Talked about performance, we talked about security, scalability, things like that. Examples of design decisions. What's important here is that we document the decision making, not just the decisions. Here you can see some examples of something that is still an architectural decision, but it's not at the top level, so to speak. Here we can talk about how are subsystems distributed? How are they deployed? Are they deployed on different servers, different machines? We can talk about using different technologies for different subsystems. There are many examples where you use different implementation languages, for instance, with different parts of the system. You pick a language that is best for a specific, the specifics of a subsystem, not the system as a whole. So, what you see in architecture documentation is primarily two strategies to reduce the complexity. The first one is abstraction. An abstraction, we have structural and behavioral abstractions. That is that we reduce information. As I said before, we don't talk about how subsystems are realized. We talk about responsibilities, the responsibilities for these subsystems, what we expect from them, what they provide in terms of services to the outside. That means that, well, if we assume that the subsystems deliver as promised, we don't need to think too much about how they do it. So if a subsystem is responsible for maintaining information about customers, for instance, we don't care, really, if they use a relational database or some other type of technology to realize that. We're just interested in some interface that supports us with customer information, not how it's stored. But if we want to have one storage strategy for the entire system, well then it's a decision we have to make at the top level, because there are many subsystems that will possibly use the same database server. So we created an abstraction so we can look away from the how, and we can encapsulate and hide information. And that's nice, because the less information we have, the less complex something is to grasp. The problem, of course, someone will say is that, well, sometimes you actually need information about the how. Performance, for instance. Yes, sometimes you need the information about how. But you can still set a constraint on a subsystem saying that the services here should provide an answer within some fraction of time. and they shouldn't use up more resources than this. And that gives them some leeway when it comes to the implementation. As long as they deliver the functionality and the specified quality, on the system level, we can try to integrate the parts now, and the overall system will deliver functionality and quality as specified. So the local ones, non-architectural. But as I said, it can be really difficult to define what is local and what is global. We can see, and you will see this too in the coming weeks, that when we talk about patterns, for instance, some patterns exist on the architectural level, but you will also find them as design patterns. So here's some examples for system-wide decisions from the example we started last week, this greenhouse application. Decisions that must be made for the system as a whole. Security, for instance. If we have subsystems and we require that we have some kind of user authentication, well, these subsystems must, if they provide services directly to the user, see to that the user is authenticated. We must agree upon how to do this, how to manage sessions if we have something like that, and also how to manage the users. We need all these components. We need someone who's responsible for these things in our system. And we need to agree who is responsible and how do we interact with them before we branch out and start working on the subsystems one by one. Local decisions, as I said before, if we have one subsystem who is responsible for storing customer or having customer storing customer data, well, that could be a local decision for that subsystem, but it can also be an architectural decision for the entire system. If you're going to share the persistent storage, well, then it's an architectural decision, but if it's just this subsystem, well, then it's a local decision. So for a guy like Peter here, the programmer, data structures, method implementations, stuff like that, everything that is not part of the subsystem level interface is local. So, as I said, it's sometimes very hard to define what's local and what's global. But a protocol can be local, but it can also be a global decision. If it's a protocol that affects the intercommunication, if it's intra-communication within a subsystem, it can be a local decision. Okay, skip that. So, let's look at some examples here. So Mary's challenge, she's the architect. She's responsible really for taking the system and coming up with a decomposition that reduces the complexity so we can focus on the parts. But how can you do that? Well, she can have clients. They can be mobile. They can be other types of clients. There can be some kind of backend with a set of servers or a single server that provides some kind of logic for this application. And of course, there must be some do it like that, some communication or connectivity between the client or the front end and the back end here. So her first job here can be to think about what functionality should we have in this system? What type of functionality should this system support? Okay, that's more or less a traditional requirements engineering effort. Sure. But the first step then is to connect who is or who will be, and now we talk about which subsystem will be responsible for a certain functionality. And we can talk about the thickness of your client. You can have a fat client and you can have a thin client. You can have a lot of functionality on the client side. It has some advantages, but it also comes with some disadvantages. You can decide to move a lot of the business logic to the back end. Has some advantages, but also some disadvantages. But it's not just the functionality. She also has to consider all the qualities. Performance, security, usability, things like that. And the architect's responsibility is to provide a decomposition where responsibilities are allocated to the subsystems here in the decomposition that caters for functionality, that caters for scalability, that caters for security, all the qualities. And that's not an easy task. That's indeed a really challenging one. Okay, so Mary comes up with some kind of decomposition that looks like this. And you can see it, there is some API. There are a couple of client components on the side here. And this first level decomposition tells us a little bit more about the system. There is some business logic component in the back end. There is some database. There is some transaction manager, and there is a user interface thingy. So the question here is why does it look like this? Honestly, I don't know. Well, I draw this picture, but I don't know, because this is a perfect example where you don't really understand why it looks like this. Well, there are some obvious ones, like iOS, Android, Java on the left-hand side. Okay. But why do we have a user interface component? That looks kind of odd, doesn't it? Why is there a transaction manager? What is the responsibilities for that one, and why does it have those responsibilities? If you don't know, you will look like a bird's nest. You will have your jaw drop, like, what? I don't get this. If we talk about functionality, maybe it's kind of intuitive. But remember, we have these guys. We have these guys. And if we talk about scalability, what is that? How do you provide for that in this system? Well, this is an example of a missing piece in the puzzle. And that's the rationale for your decisions. The rationale that gives the background information, maybe even the discussion to some point, and the decision and its motivation. Okay? So, here we have our team, Peter, Paul, and Mary. Views and viewpoints. Remember that we need to document our architecture or communicate our architecture in different ways. Mary, she has to communicate it in some way to Peter and in a different way to Paul. So who are the stakeholders here? Who are the stakeholders in this example? That was a question.
As a greenhouse?
The system itself, nah, not really. But who are the stakeholders in this project? The manager, sure. Who else?
She is.
Mary is, okay. The architect. Who else? The programmer, sure. They are all stakeholders. Even the architect is a stakeholder because, well, remember, architecture is relevant throughout the life cycle, and a year from now, it might be that Mary is now the manager and someone else is the architect. So you need certain views to deal with the concerns that an architect has. Okay? So just quickly, think about the concerns for each of these stakeholders. The third step, when you know to whom you communicate and what you communicate, you can start thinking about how should you communicate, which in our case, since we're software engineers, we love models. Models of software, I should say. So we create models. And a model can be anything from a textual description to a UML model, to a formal model, or some analytical model, or a MATLAB model, or whatever. Anything that communicates something that it's useful for the stakeholder to understand how the system deals with their concern. Whoops, that was quick. So we talked about decomposing a system into subsystems and subsystems into additional subsystems. That's a decomposition strategy. And I would say that that is useful for some of the views. but not all. So what we're using as our decomposition strategy to reduce the complexity of the architecture document is this stakeholder, concerns, and views. So think of it as a book where each chapter contains something that is relevant for one stakeholder or that stakeholder has an interest in. In this chapter, you will talk about different concerns that the stakeholder has an interest in. And for each of these concerns, you will provide a set of models that describe how this architecture addresses the specific concern. So, let's see if we can take a short break here. I'll be back in, say, 10 minutes or so. So, 12 past. Okay?
Yes.
Good? Okay, so let's move on and look at the rest of the slide deck here. So we're talking about views and viewpoints and the importance for the various stakeholders, that they get something that is tailored for their specific concern and their specific knowledge, really, and capacity. So look at Peter here, the programmer or developer, whatever. What is he interested in? Well, as a coder, he wants to think about the code view, how to organize the code, how to split them up, and how to use interfaces to interact in between the components. He should also be interested in a test view. Okay, test view. What do you mean? What is the difference between the live system or the real system, the deployable system, and the test system? Well, you know that, well, for testing a system, you need to add instrumentation. For monitoring, you need to develop test drivers, mocks, things like that. Well, that is something which is complementary to the core functionality in the system, but it's still something that, well, must be or deserves a specific model, a specific set of models, a specific view, because it's different than the other concern. Okay. Paul, then, our manager. Well, Paul, this is a very simple example, but he's actually interested in work plan, and he's interested in work division, and he's interested in economics, and he's interested in quality. So what is the manager view then? Is the Gantt chart part of the architecture? Nah, Gantt chart is not. Not the PERT either. So what could be of interest to this role, this stakeholder? Okay, yeah?
Use cases?
Sure, use cases could be something. A component decomposition where you identify the various subsystems, that could also be interesting. Test view, not necessarily the same level of detail as Peter, but he's interested in quality. So how do we assure quality in our system? How do we achieve that? Well, that's something that we could create a special view for. So the message here is really that yeah, not everything is architecture, but you have to think about the stakeholders and their concerns before you decide if something should be in the documentation or not. Users, different stakeholders, but, well, they could be interested in a functionality view, of course. They could be interested in the hardware requirements, if you have such on your system. How should you install them? Install it? Well, if it's a monolith running on a machine or an app or something like that, well, maybe not necessary then. Then it's not a concern of the user how to install this. But if it's a system of some complexity where you have distributed, several distributed processes running, you have to deploy executables, various machines, you have to install systems and libraries, and well, according to some set versioning, etc. Well, then it's a concern for the user. If we include the, well, system administrator at the customer side as a user. Still, remember this. Have a look at your stakeholders before you make a decision if they should be in or not in the architecture documentation. And for Mary, well, we talked about decomposition, but it's also all these decisions that leads up to what we call the trade-offs. Because Mary's challenge here is not to support that single quality or that other quality. Her challenge is to find a fine balance between all qualities, including functionality, in the system. And that's not a straightforward task. So it might be the case that we have to provide views that addresses more than one concern. How do we deal with performance connected to security, for instance? So the trade-offs are important here. Finding a balance between, I shouldn't use conflicting really, but it says conflicting here. What we have here is competing. Because what is a computer system? Well, a computer system provides resources for computation and resources for communication and resources for storage. 3 types of resources. But if we want, for instance, lots of performance, one strategy could be to provide much more of these resources. More computing devices, more storage, faster, better communication resources. But that's not a free lunch. That comes with a cost. Okay, the alternative, we want to cut down on costs. So we cut down on the resources, the amount of resources, and the capabilities of these resources. Now suddenly performance might become an issue. So, as an engineer, we're looking for the good enough to support both cost and performance. And that's the trade-off. You trade some performance for some cost, or you trade some cost for performance, balancing the two. The goal is always to provide something that is maximizing value for all stakeholders. There is even a methodology called the win-win, trying to create a feeling of being a winner, not just among the ones that has purchased and use the system, but also among the ones that develops the system. Every stakeholder should leave the project with a feeling of a winner. If you succeed with that, well, you will have happy coworkers, and you will also have returning customers. If you have a customer who leaves a project feeling like a loser, not likely that they will return. So, trade-offs are important because all the decisions, they are guided by our experience, they are guided by the domain we're currently working in. We perform these nice reasoning and analysis activities, but at the end of the day, it's a bargain. We need to discuss this or that, or how to combine the two. into one. So the challenge here is the as-is and to-be documentation perspectives and the decisions that lead up to this architecture. The decisions, the motivation for these decisions, and that include the trade-offs. Because as you saw with the example for this Mary decomposing the greenhouse into some components for a front end and a back end, and then, well, what is the rationale? What are the trade-offs? If you don't get the full story, just the beginning and the end, it will be difficult to change the story if the beginning changes, but the end should be the same. So this is the documentation framework. We saw that last week, stakeholder concerns and views. And well, if we look a little bit closer at this, you will see that it includes something called a viewpoint. A viewpoint in the middle sits in between the concern and the view. So a viewpoint is in principle a ready-to-use view, or view class, I should say, that you can use to instantiate a view. So someone has actually thought about, okay, these guys, they have to document the performance concern. Not just for one system, but for many systems. And we can package models in this viewpoint that then can be filled out by the architects when they create a view. So this is like a cookbook with a recipe that you work with and you follow, and at the end of the day you created a view. Oops, sorry, this one looks a bit odd. I rescaled the pictures this afternoon and I should have checked them all. But this is summarizing the text from the standard about stakeholders and their concerns. And this is summarizing what a view is. And you can see that each view addresses one or more of the concerns of the system stakeholders. So it describes a perspective, a partial view on the system. So some people explain the view using the house, well, an office building or a residential building or something like that to illustrate what an architecture is and what an architecture view is. Okay. If you visit the municipality or typically the city library, from time to time you will find exhibitions about new areas they are planning in the city with building models. You can see the streets, you can see the cars, parkings, everything there. That is an architectural view, which is used to communicate with you. You're not necessarily interested in a blueprint, because that doesn't communicate well with you when you walk by this exhibition inside the city library. But That is, of course, not the only view on this new neighborhood that the municipality is planning. There are other. There are drawings showing the buildings from the outside. There are floor plans. There are plans for the plumbing inside the buildings, but also to connect the houses, fresh water, sewage, electricity, things like that. There are drawings. Different views, different concerns, different stakeholders. I'm not that interested in the sewage plan if I'm interested in an apartment. I'm more interested in the view. What's next to that apartment? If I go out on my balcony and there is a building 2 meters away, that's the type of things I'm interested in. And for that, the model communicates fairly well. The model at the City Library. So we need something similar for our software systems. Something that we can use to communicate with our potential users. Something we can use to communicate with the decision makers. Something that we can use to communicate details, technical details, to our plumbers, to our electricians, etc., etc. So, as I said, a viewpoint here is something that is a class that we can instantiate as views. So it describes to us, use these models. And you use these models like this. So these models here all model some aspect of a concern. Some aspects can be modeled using very general languages. Others require more specialized languages. There used to be a huge surge for something called architectural description languages. That was at the beginning of the whole idea of thinking about it as a software architecture. Over the years, you have seen a decline in that interest, but there are still some architectural description languages around. You'll find some in the literature, but an architectural description language is any language which can be part of a view and communicate with stakeholders. Some of them are generic, others are very specific. So back again to this, how do I create a view? Look for your stakeholders and look for their concerns. And then make a decision on which models to use in your views. And of course, this is also something that is not carved in stone. So if you find out that this stakeholder doesn't understand, he doesn't understand, well then you need to add something. Then it could be that another stakeholder, she understands. But still, the goal is to communicate with all stakeholders, not just a majority, or worse, a few of them. So, which models do I need? Well, depends, of course, what you would like to communicate and to whom. So what type of architectural languages can we then use in our models? Well, a good candidate here is the UML. This slide is a bit old, but still it's relevant because I don't think that they have changed that much. But UML can be used to model a lot of things. Okay, someone might say, should we use UML state machine diagrams to model this aspect or that aspect? It depends. It depends on what you want to communicate and to whom. If you're communicating the functionality of your system to an end user, a state machine is probably not a wise decision. But if you're communicating how competing processes in your system should work together, maybe a state machine is useful. If you want to communicate a protocol or some other process that your system should support, maybe it's useful. So you don't communicate too much because remember, complexity comes from information. So if you have unnecessary information in your views, you will just create unnecessary complexity for the stakeholders. So keep it slim. Sometimes a simple sketch with boxes and lines, good enough. Sometimes a state machine. Sometimes a class diagram with object diagrams and state machine diagrams together do the job. But it depends on the concern and the stakeholder. So, just want to talk briefly about UML component diagrams because they, at the end of the day, when people hear the word software architecture, for some reason they always start with this decomposition into components, into subsystems. Always. And by always I mean in 99.999 or something like that of the cases. And boxes and lines are fine, but why not use a standardized diagram type when we have one? We all know that a common language is a nice foundation for a common understanding. If we speak different languages, or if we use different languages, or if we draw differently, we have to start all the time with explaining the language. What do you mean by that box? That filled arrow, what does it mean? You have that circle there. What is that? If you have a standardized language, you don't need that. You don't need to explain. And component diagrams are simple, but still useful. So a component is a part of a system that implements a set of services. And in order to implement those services, it might also require services from other components. Another thing is that it's an encapsulation. It's an abstraction that encapsulates behavior, which means that we can actually replace it with another component that provides the same type of service. So they are interchangeable in that sense. Example, an operating system a database manager system, we can in fact replace one database management system for another as long as we get the same service from it. Same with operating system. And there are, of course, many other examples where this is interchangeable. The success factor here is the interface. Books have been written on how to design good interfaces. API design. You can find lectures on the internet on how to define an interface. That is critical for the success of your decomposition and your individual component. So the diagrams here in UML, they are, of course, described as a UML model, a class model here. And you can see that you have a recursive relationship where you see that a component can be implemented by means of one or many other components. But at some point, a component can also be a class, because a class is just another abstraction that provides services while requiring services from other classes or components. So you can use this to decompose, creating a hierarchy of components. There is some more terminology to it here. We talk about ports, we talk about connections. Those are like the interfaces that our components exhibit. We have something called inner structure, which is which components / classes makes up the realization of a component. And a very simple example could look like this, where you have one component that is made up of 3 components, and you have some interfaces, and you have some inner components like a database for attractions and another one for bookings. A very simple example where, if you know the notation, I don't need to explain it more than this, and you guys can have a look at it and you can say, maybe you should have another port here supporting this one, blah, 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 blah. We don't need to start our discussions with trying to figure out what the notation is all about. So, we're closing in on the final slides here. Think about the same concern system functionality. Think about 3 types of UML diagrams. Which concern, which stakeholder could you imagine that a use case diagram would be of an interest to, or could be useful? We mentioned it a couple of times, yes, for the functionality. What else? To whom? Who are the stakeholders who would be extremely, well, would be happy, satisfied if they see a use case diagram? What is the advantage of that diagram?
Management.
Yeah, upper management. Well, I would say that since the use case diagram is really, the learning curve is not that steep. You have the stickman, you have the blobs, and you have the connection in principle. And that is what you need to understand, because the only thing it communicates is that any user of this kind have access and can use the high-level functions of the system that we have on this side. Okay. A class diagram. Stakeholder. A programmer? Sure.
Also a manager.
A manager? Maybe. Depends on, well, where she sits in the hierarchy. Who else?
Architect.
Architect, sure. Who else? Tester? Sure. What you can see is that class diagram is relevant, but not necessarily the same class model. So the tester has some interest. Maybe, well, classes that are part of the testing effort, connecting with classes in our sort of say core functionality. So the view here we create is a view on the system which is relevant for a specific concern. So just because we're using the same notation doesn't imply that we have exactly the same information. So a deployment diagram then. Who has an interest in the deployment diagram?
The architect.
The architect? Yeah, that's, come on, yeah. That's yeah. You used up your opportunity to use the architect as an answer. Okay. Who else? Who?
After development, like the ones.
Yeah, after development, who can be interested in that? Operations guys? Sure, why not? Testers. Testers are interested in deployment. Because as a tester, one of the tasks you will face is to figure out how to set up the staging environment where you can test the system as a whole or parts of the system to make sure that the integration of the already tested components work. But if you don't know what the environment looks like where the system will eventually be deployed, well, it will be challenging for you as a tester to come up with something that comes close enough to the deployment environment. So what's important? Again, think about what you want to communicate and to whom. Who is interested in this concern? What are they interested in? What type of models can we use? And then fill out the models or fill the models with the relevant information for that concern, for that stakeholder. Might well be that some views are relevant to many stakeholders. So, how many views do you think we will have? After listening to my argumentation on today's lecture, it should be thousands. Combinatorial explosion. That's not, of course, what we strive for. Again, keep it simple. You need to find some trade-off. If you have 300 views, who will be responsible for maintaining the views? That will be a mess. The probability that something will be outdated, obsolete 5 minutes after it was created is huge. So keep it a little bit simple. See if you can find a trade where you create something that communicates something to more than a single stakeholder. Focus on the things that are really relevant for the architecture level. I often see documentation that dives into the details that are not architecturally relevant, that are more detailed design decisions. So if you read the book here, they talk about view systems. There are a couple of famous view systems. One was developed by IBM in the 1990s. It was created by Philippe Kruchten, so it's named after him. It's a 4+1 view model. It has 4+1 views, and Kruchten, he claims that we can use this to communicate any aspect, any concern to any stakeholder or any system. Why? Well, if you go into these views, and you will see that this guy, he actually combines things. He speaks, he communicates with many stakeholders, many concerns in the same view. A simplification, sure, but that's a simplification you have to accept if you want something that should work for you in the long run. So by that we have come to the end of today's lecture. Remember now, stakeholder and concerns, viewpoint and views. That's how we decompose our architecture documentation. We have to document something that communicates we should achieve this architecture, the architecture to be. That's in a development situation. But then at some point when we have made decisions and even we have implemented a system, we need to communicate the architecture as it is. And as you saw with the example, a component diagram doesn't say very much if we don't communicate why it looks like it does. Document the background information which led up to the decision, the rationale for your decisions. With that, it will be much easier in the future to make the modifications that your architecture always will face. So that was it for today. Check the Moodle page for updates. There is a submission of the first assignment. There will be another assignment out next week. We meet again, is it Tuesday? Not sure, I have to check the schedule. Okay, so see you then. Bye for now.